So this talk is about the customer repurchase intention problem. And basically what we are interested in is finding out why some customers are coming back to a business while others don't. Or in other words, how we can increase customers' repurchase intentions. And for this, we propose to analyze textual reviews. And those textual reviews are also referred to the electronic word of mouth, or EWOM for short. And our idea is to apply Explainable AI to those to generate recommendations for the business owner so that they know what they have to work on in order to make customers coming back. So the first step in our methodology is we want to learn about customers' opinions. And because we cannot look into their mind, we analyze their reviews and we try to extract their opinions from their textual reviews. So textual reviews could be things on Amazon, on Google, on TripAdvisor. And we do so by using topic modeling. And this allows us then to understand what people are talking about in those reviews and finally embed those reviews in a topic space. Very quick introduction to topic modeling. Usually we are given a collection of documents and we are trying to identify a small set of topics that are discussed in those documents. And then each document, so in our case review, can be written or can be represented by a combination of a few topics. So in case of a restaurant, for instance, we might find topics like reservation issues, bad taste, or maybe some other complaints. And then a review would be like represented by a small subset of those topics. Now, with those topics in place, we can then move on to the next step, which is predicting the repurchase intention of a customer based on their opinion. So this means we take those embedded reviews in the topic space and try to classify the repurchase intention of this particular customer. For instance, if we have a customer with rather negative opinion, like long waiting time and that the food was cold, then our classifier might predict a low repurchase intention. So, and now that we have this classifier in place, we can ask why. Why was it that you predicted a low repurchase intention for this customer? And then this is where Explainable AI enters the stage. We want to find out why the classifier was predicting a low repurchase intention. And we do this by using counterfactual explanations, which I'm going to explain in the next slide. So a counterfactual explanation basically tells us what we have to change in the input, such that the output changes. The typical example is about loan application. So the customer applies for a loan at a bank, the bank rejects the application. And now a counterfactual explanation could be that it would have been accepted, this loan application, if they had earned $500 more per month, let's say. And here you can already see what makes this type of explanation so appealing, because it's very intuitive for us humans and it states a precise recommendation what we have to do in order to change the outcome into a favorable one. Now, this is nice, but we need something different because we have the problem of not wanting to explain a single customer. The business owner doesn't care much about a single customer. What they care more about is a group of customers, all their customers or their most important customers. So we need something similar. We need something where we provide the same type of explanation, but this time for a group of users, for a group of customers. And this can be done by using a somewhat novel concept called multi-instance counterfactual explanations. And those are basically recommendations that work for a set of instances or for a set of groups, for a set of users. And just to make sure, to give you a better understanding of what's going on the left plot, I have a few data points in red, and I have a decision boundary. And now I'm looking for an explanation, I'm looking for a change, how I can move those red points over the decision boundary to make them classified as blue points. And you see that for each data point, I am able to compute a vector, an error, delta. And if I apply this error to this data point, it crosses the decision boundary. And you see for these different data points, there are different errors. So this one basically focuses mostly on feature x0, while those two errors focus on feature x1. Now, this is great, but again, this is not what we want to have because it's user-specific. It's different for every customer. What we want to have is something like that. So again, we have the same setting. We have our data points here, the red ones. We have the decision boundary. And now we are looking for a single change, a single error that if applied to those instances, all those instances gets moved across the decision boundary. And you see that here we always have the same error. It's the same direction and the same length. If I apply to all my 3 data points, they all get moved over the decision boundary. This is what we are looking for. And then this can be formalized, and I did this recently and submitted this to a conference. The details of this optimization problem are not that important. Maybe the most important part is the first objective, which is about the cost. Because as you can imagine, there might be many different ways how this could be done. So which one should we pick and select and present to the user, to the business owner? Well, obviously the one that minimizes their costs, because people look for cost-efficient solutions. So I might have costs associated to each dimension. So if I change this feature, it might cost me some euros. If I change that feature, it costs me a different amount of euros. Then I could use this information to build a cost function that guides the explanation, the recommendation towards a cost-efficient solution. Now, with that having said, we can take a look at the big picture. So again, there are 3 steps. In the first step, we take the textual reviews and we try to extract customers' opinion from them by doing a topic modeling analysis. Once we have done this, we can then build a classifier that is able to classify or to predict customers' repurchase intentions. Once this is done, we move on to the last part, and this is where Explainable AI comes into it. We look at groups of customers that have all a low repurchase intention, as predicted by this classifier, and we want to explain its prediction. We ask, okay, why was it that you predicted a low repurchase intention? And this is then where we use the multi-instance counterfactuals I was just presenting on the previous slide. So we did a small case study, which is kind of a proof of concept, where we applied this methodology to a data set from TripAdvisor for restaurants on Cyprus. We used LDA, so the latent directly allocation for topic modeling, together with XGBoost for a classifier. And what we found out is that our method is able to generate reasonable results. So it was able to identify reasonable looking topics, which are depicted here, and on my poster you can also take a look at that, as well as the final recommendations are somewhat reasonable to lay users. So in this case, there was a large group of users called Group 4, and for those customers, long waiting time, quality of food, and the friendliness of the staff seems to be the big issue that the business owner should address. Now, with that having said, I'm done, and if you have any questions, feel free to ask me now during the coffee break or maybe at my poster tomorrow. Thank you very much.
Thank you very much for putting up with the delay. So at least one question, and then we'll be free for the coffee break. Come on, guys. Don't be shy. Oh, thank you very much. Oh, we got 2 volunteers. For stupid reasons, I'm going to go to the one further away from me. Oh, yeah, thanks. And try not to fall in the trap, though. Where were you? Oh, yeah.
Thanks. So, question is really simple. Like, let's say that if I use a transformer to encode the review, clearly I have a lot of dimensions there. Like, how will this thing scale with this, like going in a really high number of dimensions, no? Because then you need to look for a lot of things.
That's right, and there's also a much more important thing is that this is interpretability. So we picked LDA for a reason, because it gives us interpretable topics. If you, for instance, would use a transformer model, it would also compute an embedding, but those dimensions of the embedding, they don't have necessarily a meaning. But those meanings are important because counterfactuals, they use basically the feature values as a vocabulary in the explanation. You can think about it like for images. In case of an image, the features would be pixels, but pixels are meaningless. So you have to go like for some kind of abstraction level. And with LDA, it was possible to do this. For transformers, we tried out a few simple models, but they were not interpretable at all.